You hear that Proxima b is the nearest exoplanet, and your brain quietly files that under kind of close. Near a star, next door, just 4.24 light years away. Sounds almost friendly. The problem is, the numbers behind that phrase are so big that your intuition basically breaks. But before we continue, please subscribe to the channel to give your support. Let's continue. So first question, how far is next door really? Proxima Centauri, the star Proxima b orbits, is about 4.24 light years away. A light year is not a time, it is a distance. It is how far light travels in 1 year, moving at around 300,000 kilometers every second, about 186,000 miles every second. When you multiply that out, 1 light year comes out to roughly 9.46 trillion kilometers, or about 5.9 trillion miles. Now, scale that by 4.24. You get a distance of around 40 trillion kilometers, roughly 25 trillion miles. That is the kind of number where your normal sense of far stops being useful. You can drive hundreds of kilometers, fly thousands. The Earth-Moon distance is under 400,000 kilometers. The Earth-Sun distance is about 150 million kilometers. Here you're dealing with 40 trillion. It's not just a bit more, it's orders of magnitude more. At that scale, the planet's own orbit barely matters. Proxima b orbits very close to its star compared to Earth, only a few million kilometers away from Proxima Centauri, while Earth is about 150 million kilometers from the Sun. But when you're already talking about 40 trillion kilometers from here to that star system, shifting a few million kilometers inside that system does not change the story. For you, sitting on Earth, Proxima b is basically as far away as Proxima Centauri itself. The important point is simple. Your nearest potentially interesting planet is not a short hop, it's a multi-trillion kilometer journey. Now, the really painful part comes when you convert that distance into time using real spacecraft speeds instead of light. Light crosses that 4.24 light-year gap in just over 4 years. No refueling, no stops, no problem. You do not get that luxury. You're limited by engines, fuel, and materials that melt and break if you push too hard. Even if you grab the fastest spacecraft you've ever actually flown, and you pretend you can hold that record speed in a straight line, the travel time is not something you can fit into a human life. Look at the Parker Solar Probe. It's currently the speed record holder. At its closest approach to the Sun, it reaches about 191 kilometers per second. That's around 687,000 kilometers per hour, about 427,000 miles per hour. In everyday terms, it could cross the width of a continent in seconds. But compared to light, it's still slow. Its top speed is less than 1/10 of 1% of light speed. In fact, around 0.064%. If you take the distance to Proxima Centauri, 4.24 light years, and divide by that tiny fraction of light speed, you get a travel time of roughly 6,600 years. So even if you somehow built a probe that could cruise at Parker's absolute best speed the whole way, no deceleration, no gravity losses, no course corrections, you're still talking about more than 6 millennia to reach that star. And remember, Parker only gets that speed by diving extremely close to the Sun and using gravity to help. For a straight interstellar cruise with real mission constraints, you'd probably end up slower than that, not faster. So already, with your best real-world number, you're well beyond any single human lifetime, beyond any nation's lifespan, and getting close to the entire span of recorded history. Then you step back and ask a second, sharper question. What if you tried this with the technology that actually took humans somewhere, not just probes? That brings you to Apollo 11 and the Saturn V rocket. The Saturn V could push the Apollo spacecraft to about 11 kilometers per second as it escaped Earth, around 40,000 kilometers per hour, about 25,000 miles per hour. For going to the moon, that's enough to cross about 384,000 kilometers in roughly 3 days. For Proxima, that speed is almost meaningless. If you took that sort of velocity and stretched it across 4.24 light years, you land in a completely different time regime. Rough estimates say an Apollo-style mission to Proxima Centauri would take on the order of 43,000 years. That's not a mission where anyone remembers the launch when the ship arrives. 43,000 years ago, your species didn't have cities, didn't have writing. Global sea levels and climate were different. When you talk about flight times that long, you're not planning a mission at all. You're describing a timeline where multiple civilizations could rise and fall while one vehicle crawls between stars. Now bring in the third data point, Voyager 1, the farthest actual object you've sent out. Voyager 1 has been flying since 1977. It's moving at about 17 kilometers per second relative to the Sun, roughly 61,000 kilometers per hour, about 38,000 miles per hour. It's already crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium. So in that sense, it's in interstellar space. That sounds like progress toward the stars, but in terms of distance, Voyager is only about 26 billion kilometers from Earth. That's roughly one light day. When you put that next to 40 trillion kilometers, you see the scale problem clearly. There's a factor of more than 1,000 between one light day and 4.24 light years. If Voyager kept flying at its current speed directly toward Proxima Centauri, it would take over 70,000 years to get there. That's nearly twice the already huge number you saw with Saturn V-class speeds. So right now, your actual proven hardware gives you 3 anchors. With Voyager-class speeds, you are at around 70,000 years to Proxima b. With Apollo-era crewed rocket performance, you are in the 40,000-year range. With a very specialized sun-skimming probe like Parker at its best, in an idealized straight shot, you are still at 6,000 plus years. None of that comes close to anything you would call a trip in normal language. It is more like a slow-motion drift across history. This is why the final, deeper question in this section matters more than any single number. When you ask, how long would it take us to reach Proxima b, you are not really just asking for a travel time. You are asking how far you can push propulsion physics beyond chemical rockets. You are asking whether you can move from explosive fuel to nuclear reactors, to fusion, to lasers pushing sails. You are asking whether you can keep machines alive and functional for centuries, whether you can protect them from radiation, micrometeoroids, and simple wear. You are also asking, indirectly, how long a technological civilization like yours can stay stable, focused, and willing to pour resources into something that only pays off for people many generations down the line. So the honest takeaway at this first stage is blunt. With the speeds you have right now, Proxima b might as well be locked behind a wall of time, thousands to tens of thousands of years thick. The distance is fixed. The physics of light speed is fixed. What is not fixed is your propulsion, your engineering, and your willingness to build something radically better. And that leads straight into the next problem. If the prize at the end of this ridiculous distance is Proxima b, what exactly are you aiming for? And why does that world matter enough to even start thinking about crossing 40 trillion kilometers? You have this distance to cross, tens of trillions of kilometers. So the next question is obvious. What exactly is sitting at the far end that makes you even think about trying? Proxima b is not just some random rock. It is the first place outside your solar system that even looks like it might be in Earth's weight class. So what is Proxima b in plain numbers? Current data say it is a roughly Earth mass planet with a minimum mass of about 1.1 times Earth's mass. Minimum matters because the detection method gives you the lowest possible value, but you are clearly not dealing with a gas giant. It sits in the Earth to super-Earth range, where solid ground and an atmosphere are at least possible. It orbits a small red dwarf star, Proxima Centauri, at about 0.048 astronomical units. 1 astronomical unit is the Earth-Sun distance, around 150 million kilometers. So Proxima b is only about 7.2 million kilometers from its star, roughly 4.5 million miles. Because Proxima Centauri is smaller and cooler than the Sun, that close orbit does not automatically fry the planet. A red dwarf gives off less total energy, so the region where a planet could have liquid water is pulled in close. Proxima b sits in that band. It completes one orbit in just 11.2 Earth days. On Proxima b, a year is less than 2 weeks long. At that distance, tidal locking is very likely, meaning the same side always faces the star, like the moon with Earth. One hemisphere would see permanent day, the other permanent night, with a narrow twilight ring in between. So why does this specific world matter so much? The key is the combination. The mass is in the right ballpark for a rocky planet. The orbit sits in the star's so-called habitable zone, the distance range where, if the atmosphere is right, liquid water could exist on the surface. The whole system is only about 4.2 light-years away. Put that together and you get a planet that is Earth-ish in mass, in a maybe habitable energy zone, and extremely close by cosmic standards. That is why Proxima b became the default answer when people ask, if we ever go to another star, where do we go first? Next question. How do you even know Proxima b is real when nobody has imaged it directly? You didn't see a little dot next to Proxima Centauri. Astronomers detected it using Doppler spectroscopy, the radial velocity method. As Proxima b orbits, its gravity tugs on the star, making the star move in a tiny orbit too. From Earth, that motion means the star very slightly moves toward you and away from you. That motion imprints itself in the star's light. When the star moves toward you, the light shifts a bit toward the blue end of the spectrum. When it moves away, the light shifts toward the red. Sensitive spectrographs can measure those shifts. In Proxima's case, the wobble speed is only a few meters per second, walking speed on a star more than 4 light-years away. Years of observations showed a repeating signal every 11.2 days, exactly what you expect from a planet in a stable orbit. The size of the wobble tells you how strong the gravitational tug is, which gives that minimum mass of about 1.1 Earths. So you have an Earth-scale planet, very close to its star, in the right energy band. The next question hits hard. Is this a second Earth or a trap? The trap comes from the star. Proxima Centauri is not a calm sun twin, it's a flare star. It regularly throws off intense flares of X-rays and ultraviolet radiation, far more violent relative to its steady output than what the sun usually does. Proxima b, only 7.2 million kilometers away, sits in the middle of that storm. Over billions of years, that kind of high-energy blast can strip away a planet's atmosphere, molecule by molecule. Some models say Proxima b could have lost the equivalent of an Earth's ocean's worth of water, or even several oceans, blown into space by flares, stellar winds, and charged particles. If the atmosphere started thin, or the magnetic field was weak, you might end up with a dry, airless rock locked with one hot, blasted side and one frozen side. But there's also a less bleak option. Other simulations show that if Proxima b began with a very thick atmosphere, or has a strong magnetic field, it could survive the flares. A dense atmosphere can move heat from the day side to the night side, smoothing out extremes and keeping liquid water stable somewhere on the surface. In that scenario, Proxima b would be a harsh but active world, with permanent day, permanent night, and the ring-shaped terminator zone where conditions are more moderate. Right now, the data you have aren't enough to choose between these pictures. You know the neighborhood is hostile. You don't know whether the planet is dead or just tough. So how does all this connect back to the travel time question? Because the longer you take to get there, the more time the star and the planet have to change. Surface conditions can drift as gases are lost and chemistry runs. If a probe takes 70,000 years at Voyager speeds, you are not visiting the Proxima b you modeled today. You are visiting whatever that world has turned into after another 70,000 years of flares and slow erosion. Shorter travel times do more than make the mission feel less absurd. They keep your measurements and your arrival linked. The spectra you collect now, the climate models you run, the estimates of water and air, all assume a certain level of stellar activity and gas loss. If you can get a fast probe there in a few decades, or a slower one in a couple of centuries, there's a good chance the real planet still resembles the one you planned for. If you need thousands of years, you're effectively throwing a dart into the deep future and hoping the target is still recognizable. That is the real tension around Proxima b. It's close, it might be rocky, it might sit in a narrow habitable band, but it orbits a violent little star that is trying to strip it bare. You cannot yet see its surface. You do not know if it holds on to air and water. The prize at the end of those 40 trillion kilometers might be a battered world or a dead cinder. The only way to know for sure is to close the distance fast enough that the planet does not change beyond recognition before you arrive. How fast can you actually move when you push your engineering as hard as you know how, right now? Not on paper, not in science fiction, but with real metal that has already flown. That is where the speed record comes in, because it tells you what today can really do against that 40 trillion kilometer gap to Proxima b. The fastest object you have ever built is the Parker Solar Probe. At its peak, near its closest point to the Sun, it moves at about 191 kilometers every second. That's roughly 687,000 kilometers per hour, about 427,000 miles per hour. At that speed, a trip from New York to Tokyo would take around a minute, maybe a bit more, depending on the route. Commercial jets take over 12 hours for that, so you're beating them by a factor of hundreds. Parker reaches that speed by diving deep into the Sun's gravity well, again and again, and using Venus for repeated gravity assists. It's not just firing a rocket once and coasting, it's falling toward the Sun, swinging past and converting that fall into raw speed. That sounds extreme, and for the solar system, it is. No human crew has ever moved that fast. No other probe has hit that velocity. This is your current high score, a real measured number, not a proposal on a slide. If you want to know what your civilization can actually do with clever use of gravity and current propulsion, Parker is the benchmark. The next question is simple and brutal. How good is that when you compare it to light itself? Light moves at about 300,000 kilometers every second, around 186,000 miles per second. Take Parker's 191 kilometers per second and set it next to that. You get roughly 0.064% of light speed. In other words, Parker is doing about 0.06% of the universe's speed limit. If you want a simpler way to say it, imagine light taking 1 second for some stretch of distance. Parker would need around 1,500 seconds to cover that same stretch. Now connect that to Proxima. The star is about 4.24 light-years away. A light-year is how far light travels in a year, so light needs just over 4 years to reach Proxima Centauri. Parker, crawling along at about 0.00064 of that speed, would need much, much longer. When you divide 4.24 by that tiny fraction, you get a travel time of about 6,600 years. And that's a best-case, straight-line, constant speed estimate. No slowing down, no extra course corrections, just go. 6,500 years, using the fastest speed you have ever actually achieved with hardware. So, of course, the next question is Parker a one-off freak case, or is there a whole lineup of craft clustered in some range of speeds that tell you what is normal? When you check the rest of the leaderboard, you see a clear pattern. Before Parker, the record holder was Helios 2, a solar probe launched in the 1970s, which hit about 70.2 kilometers per second, roughly 252,000 kilometers per hour, about 157,000 miles per hour, also by diving close to the Sun. Then you have the famous deep space probes, Voyager 1, Voyager 2, and the Pioneer probes. Out in interplanetary space, their cruise speeds sit between about 10 and 17 kilometers per second. That's around 36,000 to 61,000 kilometers per hour, roughly 22,000 to 38,000 miles per hour. They got those speeds by stacking chemical rocket burns with gravity assists from giant planets like Jupiter and Saturn. Put those numbers together and you see the real picture. With chemical propulsion plus the smartest gravity assist tricks you can manage, you consistently end up in the band between about 10 and 70 kilometers per second. Parker stretches it to about 190 kilometers per second only because it's designed to skim very close to the Sun, in brutal thermal conditions that no normal mission could tolerate. For most missions, the safe, usable range sits much lower. So what does that leaderboard really mean when you talk about going to another star? Groups like Breakthrough Starshot have laid it out very plainly. If you take the kind of speeds you get from current chemical rockets and gravity assists, and you scale them up to the distance to the Alpha Centauri system, you land in the tens of thousands of years range. Some back of the envelope calculations put it at 30,000 years or more. That is not someone being negative for drama, that is what happens when you take real velocities, the ones you know how to achieve now, and stretch them across 4 point something light years. Even if you lean on Parker's top speed instead of the more typical numbers, you still only drop the travel time from tens of thousands of years down to several thousand years. It is better, but it is not good in any sense that matters for humans. And remember, Parker's performance depends on orbiting the sun again and again, getting cooked and using that orbit geometry. A direct Proxima B mission would not have the same profile. So if you walked into a space agency today with unlimited money and said, launch an interstellar probe to Proxima B using only technology that has already flown, what timeline are you really agreeing to? Realistically, you would design a probe with the best chemical engines you have. You would stack up gravity assist from Earth, maybe Jupiter, maybe dive near the sun, and you might squeeze your way into the higher end of that 10 to 70 kilometers per second band, maybe a bit more if you are very aggressive. Then you point that thing toward Proxima and let it go. The result is still travel times in the tens of thousands of years. Maybe you are closer to 20,000 than 70,000. Maybe you find an extremely clever trajectory, but you are not getting it down to hundreds of years, let alone decades. By the time the probe reaches Proxima B, every country on Earth will have changed. Your languages will have shifted, your technology will be unrecognizable, and your descendants may not even remember who launched it, unless they maintain records for longer than any civilization in history has managed so far. That is the blunt launch now answer for a Proxima B mission with current propulsion, and it sets the baseline for everything that comes next. To make that travel time drop from tens of thousands of years to something humans can care about, you cannot just tweak chemical rockets a bit. You have to change the propulsion game completely, move into nuclear, fusion, or beams of light pushing sails. The speed record tells you, very clearly, that today's rockets are perfect for planets and almost useless for stars. You keep hearing just build a bigger rocket, but there is a hard limit baked into the physics, and it is the reason your fastest ships are still painfully slow on an interstellar scale. Rockets don't top out because engineers are lazy, they top out because the math is brutal. Chemical rockets work by throwing mass out the back at high speed. The faster you throw that exhaust, the more your rocket speeds up in the opposite direction. For the engines you actually use, typical exhaust velocities live in the 2.5 to 4.5 kilometers per second range. In rocket engine language, that's a specific impulse of about 250 to 450 seconds. That sounds abstract, so here's what it means when you plug it into the rocket equation. The rocket equation in words says this: the maximum change in speed your rocket can get, your delta V, equals the exhaust speed multiplied by a logarithm of how much of your starting mass is propellant. So if 90% of your starting mass is fuel and only 10% is structure and payload, your mass ratio is 10 to 1. Take an exhaust velocity of 4 kilometers per second, which is generous for chemical engines, multiply that by the logarithm of 10, which is about 2.3, and you get a theoretical maximum change in speed of roughly 9.2 kilometers per second. That's an ideal number, ignoring gravity losses, air drag, and all the real-world inefficiencies. And 9.2 kilometers per second is just enough to reach low Earth orbit, not enough to sprint to another star. Even when 90% of your rocket is fuel, the payoff in speed is modest. So the first wall you hit is simple. Your fuel gives you speed only in proportion to its exhaust velocity, and exhaust velocity for chemical reactions is stuck in the low single-digit kilometers per second. You can design smarter tanks, lighter structures, more efficient engines, but you are fighting against a logarithm. Doubling the fuel does not double your speed. It gives you a small bump, and each extra bit of fuel helps less than the last. Then there's the second wall, the gravity tax you pay just to get away from Earth at all. To completely escape Earth's gravity, you need a speed of about 11.2 kilometers per second relative to the surface. That number is not a guess. It comes straight from Newton's law of gravity, Earth's mass, and Earth's radius. It's the speed where your kinetic energy exactly matches the gravitational energy holding you down, so you climb away and never fall back. Every mission that wants to go interstellar has to pay that cost first, just to get out of the planet's grip, before you even start thinking about building up long-range cruise speed. So if your chemical rocket can theoretically deliver, say, 9 or 10 kilometers per second of delta V in an idealized case, you can see the problem. You're already spending almost all of that just to reach orbit and then climb further out of Earth's well. You don't have a lot left over for, now let's accelerate to a useful fraction of light speed. In practice, that's why interstellar mission studies don't even pretend to rely on pure chemical propulsion for the actual crew segment. It's like using a family car to try to reach orbital speed. It's the wrong tool for the wrong scale. So the next idea is obvious. Why not just stack more stages? You might think if one rocket stage gets me to orbit, then 3 or 4 stages should push me to something much faster. Staging does help, and you are already using it. A multi-stage rocket drops empty tanks and engines along the way, so the remaining stages do not have to carry dead weight. That is how Saturn V worked, and how modern heavy-lift rockets work. But each extra stage you add brings its own tank, structure, plumbing, and engines, all of which count as non-fuel mass. The more propellant you haul for later, the more structure you need to hold it, and the more fuel you need in earlier stages just to push that structure. Very quickly, you end up in a feedback loop where most of your fuel is being burned not to move your payload, but to move the rest of your fuel. Because the rocket equation has that logarithm built in, pushing your mass ratio higher and higher gives you smaller and smaller gains in delta V. On paper, you can always say add more stages, but in reality, you run into structural limits, cost limits, and launch constraints long before you get anywhere near interstellar speeds. If more fuel and more stages are a dead end, the next trick is to stop relying only on your engines and start stealing energy from the planets and the sun themselves. That is what gravity assists are for. When a spacecraft flies past a planet like Jupiter, it can swing around in just the right way that from the sun's point of view, it leaves the encounter moving faster than it arrived. You are trading a tiny bit of the planet's orbital energy for extra speed for the spacecraft. That is how the Voyager probes and Helios 2 boosted their velocities without carrying impossible amounts of propellant. Parker's solar probe takes this even further by diving very close to the sun, dropping into the sun's gravity and converting that fall into enormous speed. Gravity assists feel like free speed, but there are catches. You only have a few massive bodies to work with, and they are on fixed orbits. To get good boosts, your launch windows and flyby paths have to line up with those orbits. You can't just chain an unlimited number of assists in any direction you like. At some point, you exit the region where any planet can help you. Once you're on an escape trajectory out of the solar system, gravity assists are over. From that moment on, you're back to whatever speed your last burn and last slingshot gave you, and any further changes come from slow, incremental pushes, not big free boosts. Put all of this together, and then ask the uncomfortable question. What does this mean for getting to Proxima B using chemical rockets only? Even with perfect design, aggressive staging, and the best possible gravity assists, you're not going to sustain more than a few dozen kilometers per second of cruise speed. People sometimes throw around an optimistic number like 100 kilometers per second, which is about 360,000 kilometers per hour, roughly 223,000 miles per hour. That is far above what you usually fly, and already extremely hard to reach with real vehicles and fuel. Now compare that 100 kilometers per second to the 40 trillion kilometer distance to Proxima Centauri. Divide that distance by that speed, and you get a travel time of roughly 12 to 13,000 years. So even at that very optimistic chemical plus gravity limit, you're still staring at a 5-figure year count. If you drop back to more realistic cruise speeds in the 10 to 70 kilometers per second range, the numbers go up into tens of thousands of years, like you saw with Voyager-class trajectories. So the bottom line is sharp. Chemical rockets, even at their absolute best, are fantastic for getting you off planets, into orbit, and around your own solar system. They are the right tool for Mars, Jupiter, Saturn, and even deep Kuiper-belt missions. But on interstellar distances, they are catastrophically bad. They hit a ceiling imposed by exhaust velocity, gravity, and the rocket equation itself. If you want to turn Proxima b into a thought experiment into a destination, you have to get away from chemical propulsion entirely and start tapping much more energetic engines. So if rockets that burn chemicals hit a wall, what is the first truly different thing you can bolt onto a spaceship to punch through that limit? The next step up is simple in concept and nasty in detail. You stop burning fuel and start running a reactor in space. You turn a nuclear power plant into a rocket engine. The core idea of a nuclear thermal rocket is direct. Instead of burning hydrogen with oxygen, you run liquid hydrogen through a fission reactor, heat it until it's insanely hot, and throw that out the back. The hotter the exhaust, the faster it leaves, and the faster your ship can go. With nuclear thermal engines, you're not stuck at chemical exhaust speeds of around 2.5 to 4.5 kilometers per second. You can push the exhaust velocity up to roughly twice that. In engine terms, your specific impulse jumps from the 450-second range to something like 800 to 1,000 seconds. That means for the same mass ratio, the same how much of this vehicle is fuel number, your maximum change in speed, your delta V, roughly doubles. That's the first big shift. You're not changing the rocket equation, but you are finally feeding it better numbers. So if nuclear thermal is about brute heating, what's the twist that comes next when you ask, can I push that even further by being patient? That's where nuclear electric propulsion comes in. Here, instead of blasting hot gas out of a nozzle, you use a reactor to generate electrical power, and that power runs very efficient electric thrusters, like ion engines or Hall thrusters. These engines push out ions, charged atoms, at tens of thousands of kilometers per second, far faster than any chemical exhaust. The trade-off is that the thrust is tiny. You're not getting the shove of a Saturn V, you're getting a gentle, constant push, like slowly nudging a shopping cart forever. Ion drives have already flown. The Dawn spacecraft, for example, used ion engines to visit the asteroids Vesta and Ceres, building up a large change in velocity over months and years of steady operation, with only a small amount of xenon propellant. The key point is this. Even if each second of thrust is weak, the combination of very high exhaust velocity and very long burn time lets nuclear electric systems rack up total speed changes that chemical rockets can't touch, without needing ridiculous amounts of propellant mass. The real question then becomes, if you scale these nuclear ideas hard, what numbers do you actually get for going to Proxima? In optimistic concepts, where you accept big, heavy reactors and serious engineering risk, you might reach cruise speeds in the several hundred kilometers per second range, say 300 to 500 kilometers per second. That's 300,000 to 500,000 meters every second, or about 1.08 million to 1.8 million kilometers per hour. In miles per hour, you're talking roughly 670,000 to about 1.1 million miles per hour. As a fraction of light speed, that's around 0.1 to 0.17% of light. So you're still far below the Parker Solar Probe's eventual dream levels, but now as a cruise speed, not a brief peak. Take the upper end of that, 500 kilometers per second. Proxima is 4.24 light years away. At roughly 0.0017 of light speed, you're now looking at a travel time of around 2,500 years. That is a huge improvement over 70,000 years, or even 12,000 years. You slash the time from longer than many species survive down to longer than all of recorded human history. Better, yes, but you are still nowhere near launch this and get data back in one career. So if the physics starts to look at least acceptable, what then holds nuclear propulsion back? The first problem is mass. Reactors are not light, especially when you need them to generate megawatts or more of power reliably in space. You have to carry the reactor core, control systems, cooling systems, radiators to dump heat into space, and the structure to hold all of this together. On top of that, you must shield the crew, if there is one, and the sensitive electronics from neutron and gamma radiation coming straight out of the reactor. Shielding means thick layers of dense material like water, polyethylene, or metals, which adds more mass. More mass means you need more propulsion to get the same acceleration, which feeds right back into needing bigger reactors, bigger radiators, and more structure. You can try to solve some of this by putting the reactor on a long boom, keeping it far from the cruise section so the radiation spreads out, but the basic fact remains. High-power reactors are heavy. The second problem is safety. Putting a large fission reactor on top of a rocket and lighting the fuse is not something regulators and the public accept easily. Small nuclear power sources like radioisotope generators already fly, but full-scale reactors running at megawatt levels in Earth orbit or beyond raise global concerns. A launch failure spreading reactor debris in the atmosphere is not an abstract fear. Interstellar-class nuclear propulsion means you are suddenly mixing Apollo-scale engineering projects with Cold War nuclear fears, and that slows everything down. If reactors are heavy and controversial, why not just push harder, build the biggest nuclear ship you can, and be done with it? The catch is, even when nuclear drives work perfectly on paper, they still do not give you the kind of speed you need to reach Proxima B within a human life unless you accept extreme designs that are way beyond what anyone is building now. Nuclear thermal engines double or maybe triple what a chemical rocket can do. Nuclear electric engines can, in principle, give you larger total speed change, but at the cost of very low thrust and long travel times. So nuclear starts to look like a bridge, not the endpoint. It can cut the trip from geological time, tens of thousands of years, down to civilizational time, a few thousand years, maybe a few hundred in extremely optimistic scenarios. That is a major step, but it is still not you launch the probe, you retire, and you see the first images before you die. To get anywhere near that, you have to break an even bigger rule. You have to stop carrying almost all of your energy and propellant on the ship, and instead use something outside the spacecraft to push it. That is where fusion concepts and giant laser arrays start to enter the picture, and where the Proxima timeline suddenly jumps from never into maybe if you're willing to rebuild your whole energy infrastructure. You solve some problems with nuclear rockets, and suddenly a harder question appears. If you want Proxima B in less than thousands of years, what do you burn next? The answer people keep coming back to is straightforward and extreme. You do not burn anything, you fuse it, the same process that powers stars. So first point, what is the actual promise of fusion propulsion? On paper, not in marketing. In fusion, you slam light nuclei like deuterium and helium-3 together so hard that they merge and release huge amounts of energy. Per kilogram of fuel, fusion gives you millions of times more energy than chemical reactions. A fusion rocket doesn't just get a bit better exhaust velocity, it can, in theory, throw reaction mass out the back at tens of thousands of kilometers per second. That's a jump from single digits to tens of thousands. Concept studies like Project Daedalus and later fusion drive designs take that energy and plug it into the rocket equation. They show that at least in calculations, you could push a ship to something like 5 to 10% of light speed, maybe more in extreme cases. 5% of light speed means about 15,000 kilometers per second. 10% means about 30,000 kilometers per second. Those are the ranges where Proxima B stops being a multi-millennial crawl and starts to turn into a multi-decade mission. But is this just a fantasy, or did anyone ever try to draw a real ship around these numbers? In the 1970s, the British Interplanetary Society sat down and did the hard work on a design called Project Daedalus. It was not a sketch, it was a full engineering study for an uncrewed interstellar probe. Daedalus was huge. The plan was to accelerate a probe of around 50,000 tons total mass using a two-stage fusion drive. The fuel mix was helium-3 and deuterium, formed into pellets. Electron beams would ignite these pellets at high repetition rates behind the ship, like a rapid-fire sequence of tiny controlled fusion explosions. Each micro-explosion would heat reaction mass and push the craft forward. Over a few years of continuous burn, Daedalus was supposed to reach around 12% of light speed, so a bit faster than the 5 to 10% band you usually hear. Later fusion concepts change details. They swap confinement methods. They use magnetic fields instead of electron beams. They tweak the fuel mix. But the headline stays the same. If you can get stable, high-power fusion working in rocket configuration, then speeds of several tenths of light speed are not obviously impossible on paper. You are no longer arguing over whether you can reach 100 kilometers per second. You are asking whether you can reach tens of thousands of kilometers per second and keep a complex machine alive while you do it. So if you accept that kind of performance, what does that do to the clock on Proxima b? Take a clean, round number, 10% of light speed. That is about 30,000 kilometers per second, or about 67 million miles per hour. At that speed, the 4.24 light-year distance to Proxima b takes roughly 40 plus years of coasting, ignoring the time you spend accelerating and slowing down at the start and end. From Earth's frame, you launch, you accelerate for some years, you cruise, you decelerate, and you arrive at the system a bit over 4 decades after departure. Then your first signal back to Earth still takes 4.24 years at light speed. So the people who launch the mission wait something like mid-life, then get the confirmation. If you only manage 5% of light speed, half that velocity, your transit time doubles to something like 80 to 90 years. But even then, you are finally in a regime where a single human lifetime can at least overlap with the mission from launch to first data. That is a completely different situation from thousands of years. So, on the surface, fusion sounds like the perfect answer. High speed, realistic-looking travel times, no weird external beams. Why is this not already being built? The short answer is fuel and technology. The fuel you want for a clean, efficient fusion rocket is not easy to get. Designs like Daedalus assume large amounts of helium-3 and deuterium. Deuterium, heavy hydrogen, is common in oceans and in gas giants. Helium-3 is rare on Earth and more available in the atmospheres of giant planets, or possibly in lunar regolith at low concentrations. To load a Daedalus-style vehicle, you're talking about mining gas giants like Jupiter or Saturn, separating out helium-3 from massive volumes of gas, and then shipping it to wherever you build the ship. That alone is a huge space industry challenge, and that's before you talk about storing and handling those fuels safely at scale. Then there's the technology to actually make fusion happen in a controlled way over years on a moving ship. On Earth, big experiments like ITER are still working just to reach net positive fusion power in a stationary reactor. They are not worried about thrust, nozzle erosion, or structural shocks from rapid pulsed ignition at high repetition rates. Turning experimental fusion power plants into engines is another full level of difficulty. You need extremely strong magnetic fields, robust fuel delivery systems, precision timing, and materials that do not fall apart under constant neutron bombardment. So you are stacking challenges. 1. Get reliable, high-output fusion on Earth. 2. Miniaturize it and harden it into a rocket system that can run for years. 3. Build the supply chain to deliver exotic fuels, likely harvested from other planets, to your launch point. None of these steps are solved now. This puts fusion in a very specific place on your Proxima b timeline. It's not pure fantasy, but it's also not next decade. Fusion drives are the tool that could take you from never to grand ambition maybe. If over the next couple of centuries fusion power becomes as normal in your infrastructure as gas turbines are today, the idea of scaling that up to an interstellar drive stops sounding ridiculous. At that point, 40-year to 100-year mission durations start to move from science fiction to the outer edge of serious engineering studies. And that is the key shift. With fusion, you finally see numbers where a generation could launch a mission to Proxima b, and at least some of them, or their direct children, could still be alive to watch the first images arrive. It is still an extreme project. It still demands a stable, wealthy, technologically mature civilization, but it is not blocked by physics anymore. It is held back by engineering and will. The catch is that even fusion still carries its own fuel, its own reactors, its own mass. To push travel times down further into the low decade range or even under, you have to ask a harder question. What if the ship stops bringing almost all of its energy with it and something outside the ship does the pushing instead? That is where beamed sails and giant laser arrays enter the picture, and where the tension jumps again, because now you are not just building a spacecraft, you're building a whole interstellar launch system on and around Earth. You keep trying to solve interstellar travel by loading more stuff onto the ship, more fuel, bigger engines, thicker shields, and it keeps failing for the same reason. The rocket equation punishes you. The only clean way out is to stop carrying almost all of your energy with you and let something back home do the heavy lifting. So here's the flip. Instead of building a rocket, you build a sail. Breakthrough Starshot takes the whole fuel problem and turns it inside out. The idea is simple to say, brutal to execute. You attach a very thin, very reflective light sail, a few meters across, to a tiny payload, a wafer of electronics just a few grams in mass, something like an interstellar chip. Then, instead of burning fuel, you hit that sail with an enormous laser beam from Earth, or from a large installation in space. The sail feels the push from the photons, from the light itself. If the laser is powerful enough and the sail is light enough, you can push that little probe to something like 15 to 20% of light speed. That means on the order of 45,000 to 60,000 kilometers every second, tens of millions of miles per hour, with no propellant tanks at all on the probe. The obvious question is, does anyone have numbers for this, or is it just a cool sketch? Starshot's studies are surprisingly concrete. The concept uses a phased array of lasers spread over kilometers, all firing together so their beams add up into one focused spot. The total power output is in the range of hundreds of gigawatts, dumping around a terajoule of energy into the sail over a few minutes. During that short window, the probe experiences enormous acceleration, thousands of g, which would crush a human, but a small solid-state package can survive it if you design it right. At the target speed of about 20% of light speed, a probe could cross the roughly 4.37 light years to the Alpha Centauri system in around 20 years of travel seen from Earth. Add the 4 or so years for its laser or radio signal to come back at light speed, and you're looking at roughly 24 years between launch and first data arriving back home. For Proxima b, at about 4.24 light years, the numbers are almost the same, just slightly shorter. Suddenly, how long does it take to get there drops from thousands of years to a few decades. Another key question, what are you actually launching on that sail? You're not sending a starship, no crew cabins, no huge fuel tanks. You're sending something closer to an interstellar smartphone. The payload is a wafer-scale probe, a few centimeters across, massing maybe a few grams. On that chip, you squeeze a camera, navigation sensors, a basic computer, and a tiny transmitter. The whole vehicle might weigh less than a large insect, but moving at a speed no human has ever approached. This is why the trade-off is so sharp. You get ridiculous speed, but you only get it if the payload is tiny. You cannot do this with a 1,000-ton ship. The accelerations and power levels would be insane. So Starshot is not about sending settlers, it's about sending scouts. Fast, cheap in mass, expensive in infrastructure, and getting the first close-up pictures of planets like Proxima b. Then the next problem hits. Even if you can accelerate to 20% of light speed, what happens when you reach the target? At that speed, you cross the Proxima system very fast. The time your probe is within useful imaging range of Proxima b is measured in seconds to minutes. You cannot brake because the whole design assumes the only push comes from the launch side laser, and that laser is now many light years behind you. So the mission profile is a one-shot flyby. The probe screams in, grabs as much data as it can, and beams that back to Earth as it recedes into the dark. Other researchers have tried to soften that problem with a different trick, using photogravitational braking. In that idea, you use a much larger, lighter sail, and when you get to the target system, you turn the sail so that the starlight and the star's gravity combine to slow you down. You fall into the system, swing by the star, and let radiation pressure bleed off your speed. That can, in principle, turn a flyby into a rendezvous or at least a much slower pass. But the cost is brutal in time. Numbers for Proxima with this kind of braking land around 120 years total travel time. You lose speed, you gain the ability to stop and actually orbit or hover near the target. So you get a clear fork. With Starshot-style sail and laser, you can reach Proxima b in roughly 20 years and do a drive-by snapshot at extreme speed. Or with sails and clever braking using the target star's light, you can think about missions that take around a century but allow a more detailed, slower exploration once you arrive. Both still assume gram-scale or at best kilogram-scale payloads. You're not landing rovers or unfolding big bases. You're in the regime of small probes and carefully planned instrument packages. So why does this approach still matter so much then, if it only delivers tiny scouts? Because it's the first serious plan that compresses the Proxima clock into a human working lifetime. Using Starshot numbers, the timescale is you build the laser array, you launch a wave of wafer probes, you wait 20 years for them to cross the gap, then you wait a bit more for the light speed signal to come back. The mission scientists who proposed it could realistically still be alive to see the raw images. The grad students who helped design it could be mid-career when the data lands. That's completely different from start now, get answers in 3,000 years. Also notice what this does to the structure of the problem. With rockets and even fusion drives, the focus is on the vehicle, on the ship itself. With beamed sails, the focus shifts to infrastructure. The hard part is building and powering a multi-kilometer laser array on Earth or in orbit, with the control systems to keep a narrow beam locked on a sail that is getting farther away every second. The probe is cheap in mass, but the launcher is a mega project, on the scale of global energy systems or major military spending. So Starshot-style designs crack the timeline open in a very specific way. They do not solve colonization, they do not bring humans any closer physically, but they take the first step of turning Proxima b from a distant point in your telescope into a place you could actually see in detail, while people alive at launch are still around. And once you have the infrastructure to push gram-scale craft to 20% of light speed, the next question is unavoidable. Can you scale any of this up? Can you push heavier sails? Can you combine beamed propulsion with fusion or other drives and cut travel times further without giving up the ability to slow down? That is where the tension jumps again, because the moment you see a path to tiny probes in a few decades, the demand for something bigger, slower, and more capable goes through the roof. You finally have a way to touch another star with data, and that raises the stakes on every other technology in the queue. You can make the trip to Proxima feel shorter for the people on the ship without changing the distance and without changing the laws of physics. That sounds like cheating, but this is exactly what relativity hands you when you start moving at a serious fraction of light speed. At normal speeds, like planes or even rockets, relativistic time dilation is basically zero. You could measure it with precise clocks, but nobody feels it. Once you get up to a significant fraction of light speed, that stops being a tiny correction and starts being a real design factor. Physicists use a number called the Lorentz factor, usually just called gamma. It tells you how much slower time runs on a fast-moving ship compared to time back on Earth. The closer your speed gets to light speed, the more gamma grows. At around 20% of light speed, about 60,000 kilometers per second, gamma is only about 1.02. That means onboard clocks tick only a few percent slower than clocks on Earth. Not a big effect. But if you somehow reach 90% of light speed, about 270,000 kilometers per second, gamma jumps to around 2.3. Now the difference is huge. Anything happening on the ship takes less than half as much proper time as it does when measured from Earth. So what does that actually do to the Proxima timeline from the point of view of people on board? Say you pull off the impossible and build a crewed ship that can cruise at 90% of light speed, ignoring for a moment the time spent accelerating up to that speed and slowing down again. From Earth's frame, Proxima b is about 4.24 light-years away. If you cruise most of the way at 90% of light speed, the travel time seen from Earth is a bit over 4.5 years, something like 4.7 years. But on the ship, because time runs slower by that gamma factor of about 2.3, the crew experiences only around 2.1 years of travel. They age just over 2 years while Earth ages almost 5. Push closer to the speed of light and the effect gets stronger. The faster you go, the more you squeeze the experience duration for travelers, even though the distance and the light speed limit are unchanged. That sounds perfect for long missions, so why not just decide to cruise at 90% of light speed and be done? The price shows up when you look at energy. The kinetic energy of the ship does not grow in a straight line with speed. It grows in a way tied directly to that same gamma factor. Roughly speaking, the extra energy you have to pump into the ship is proportional to gamma minus 1. At 90% of light speed, gamma is a bit more than 2, so gamma minus 1 is roughly 1.3. When you translate that into joules, you get something like 4 times 10 to the power of 16 joules per ton of spacecraft. That is per 1,000 kilograms. For comparison, that's on the order of several thousand megatons of TNT worth of energy in each ton of ship mass. So a 1,000-ton starship at 90% of light speed is storing more kinetic energy than all the nuclear weapons humans have ever built, combined, by a large margin. It's a flying doomsday device. Not metaphorically, but in raw physics. Any failure, any uncontrolled collision releases energy on a planetary disaster scale. This is a big part of why most serious interstellar concepts stay in the 10 to 30% of light speed band. Even there, the energies are enormous, but they're less ridiculous than the 90% case. Energy is not the only problem. At high fractions of light speed, the environment itself turns against you. Hit even a tiny dust grain at 50% of light speed, about 150,000 kilometers per second, that grain slams into your hull with the energy of a small explosive. Interstellar space is not perfectly empty. There are atoms of hydrogen and helium. There are dust particles. At low speeds, they're background noise. At relativistic speeds, the sparse gas turns into a beam of high-energy particles streaming straight into the front of your ship. For electronics, it's like sitting inside a particle accelerator. For human tissue, it's a constant radiation storm. To cope with that, any real high-speed design needs serious shielding. You can put a thick physical shield at the front, you can use magnetic fields to deflect charged particles, or a combination of both. But every layer of shielding is more mass. More mass means more energy needed to reach your cruise speed. More energy means bigger engines or bigger external power sources, which means more complexity, more risk. Once again, pushing toward very high gamma values drags you into a loop of rising mass and rising energy that is hard to close. So you end up in a narrow, awkward lane. Time dilation is only weak at speeds below, say, 50% of light speed. You only start to feel serious subjective time cuts when you go above that. But once you push that high, the energy and shielding requirements shoot up sharply. Around 10 to 20% of light speed, radiation and dust are still a big problem, but they might be manageable with advanced shielding and engineering. Around 50 and beyond, all the numbers get ugly. There is another catch here that matters for planning. Time dilation is helpful for the cruise experience, but the universe does not care about how fast their watches run. The speed of light is still the upper limit for any signal. The ship could experience only a couple of years of travel time, but Earth would still watch the mission unfold over 4, 10, or 20 years, depending on speed and trajectory. And then, once the ship arrives at Proxima b, any message it sends still takes about 4.24 years to get back, no matter how time is flowing on board. Mission Control cannot speed that up. There's no way to have a real-time conversation across 4 light years. So, when you sit down to design a Proxima mission, relativity becomes a constraint instead of a magic hack. For robotic probes with no lifespan, time dilation is irrelevant. You only care how long the mission takes in Earth's frame. For crewed missions, time dilation can make the trip feel shorter for the people who go, but it cannot make it shorter for their families back home or for the civilization funding the mission. And to even reach the speed where time dilation starts to matter in a big way, around half of light speed or more, you are taking on engineering challenges that are vastly harder than building fusion reactors or multi-terawatt laser arrays. That is the uncomfortable bottom line. Relativity gives you a little help at the high end. It lets the travelers cheat on the time they personally feel, but it only starts paying off once you're in a velocity regime that is probably centuries beyond your first serious interstellar probes. For the next few hundred years, the real choice is not, do we use time dilation? It is, do we go fast enough that we can even think about crew at all? Or do we accept that humans are too slow and too fragile, and design missions that either last for many generations or freeze people in place and try to wake them up centuries later? And that's the next step in the logic. If you cannot reasonably push your ships to half the speed of light anytime soon, then your other option is brutal and simple. You do not beat the clock, you write it. You put a whole community inside a starship and let them live and die while the ship crawls across interstellar space. You can beat a 2,000-year journey with 80-year bodies, but not by speeding up the ship. So the question becomes brutal. Not how fast can you go, but can you build a world that outlives everyone on it, over and over again, while it crawls to Proxima b? Say your propulsion tech stalls out at around 0.002 of light speed, about 600 kilometers per second. That's 600,000 meters every second, around 2.1 million kilometers per hour, roughly 1.3 million miles per hour. That sounds insane compared to anything flying now, but it's still only 0.1% of light speed. At that pace, crossing 4.24 light years is not 40 years, it's closer to 2,000. You're not planning a mission anymore, you're planning a moving civilization. This is where the generation ship idea stops being a sci-fi trope and turns into the only consistent answer. Instead of a ship with a crew, you design a ship as a mobile world. Tens of thousands of people at launch, closed ecosystems, farms, recycling loops, industry, education, law, culture, all inside a metal shell. People are born, grow up, work, have children, die, and get buried or recycled, all while the ship drifts across interstellar space at maybe 600 kilometers per second. For them, Proxima b is not a destination with a date, it's a background fact, like gravity. The trip time becomes a cultural constant, not a mission countdown. Then you run straight into biology. Human bodies right now last maybe 80 years on average in wealthy countries. You can push that with medicine, gene therapy, better diets, maybe stretch healthy life toward 100 or more. But you cannot stretch a human body across 2,000 years. Entropy always wins. That's why serious thinking about generation ships doesn't focus on a crew in the usual sense. It focuses on populations and systems. You need large, stable, closed-loop life support systems that can keep soil fertile, water clean, air breathable, and food growing for centuries. You need redundancy in everything, from agriculture to power to manufacturing. You're not designing a long mission. You're designing an artificial biosphere that has to survive longer than any country on Earth has existed. Even if you boost individual lifespans with future biotech, you still have the same structure. Maybe each person sees 1% of the journey instead of 0.5%. It doesn't change the basic logic. Your starship has to be built to keep an ecosystem and a society running, not to keep a single group of astronauts alive until they get there. So of course, the next temptation is to try to hack biology directly and skip the whole multi-generation problem. Put people to sleep, send them as cargo, wake them up at Proxima. Cryogenic sleep, suspended animation, call it what you want. The idea is the same. Freeze the passengers, stop or slow their biological processes to near zero, and bring them back centuries later with the same mind, memories, and health is not something you can do. The medical problems are huge. Ice crystals shredding cells, damage to blood vessels, chemical imbalances, brain structure integrity, all under extreme cold. So any interstellar plan that quietly writes in, and the crew sleeps for 2,000 years and wakes up fine, is not a plan. It's a bet that future biology will solve multiple hard problems in time, with no guarantee. If you launch on that assumption and biology doesn't deliver, your entire mission dies in transit. For a robotic payload, you can afford to risk a new technology. For a crew of thousands, betting their lives on "we'll figure out cryosleep later" is irresponsible. Even if you somehow crack long-term hibernation or deep metabolic slowdown, you still need machines to keep those sleeping people alive for centuries, with power, temperature control, and protection from radiation. You're back to designing systems that do not fail for hundreds or thousands of years, and that brings you right back to the generation ship level of reliability, just with unconscious passengers instead of conscious citizens. Then comes the hardest part, and it is not engineering or medicine, it is sociology. A generation ship is basically a flying city, completely isolated with no outside help, no fresh air, no new land to expand into for 20 centuries. How do you stop its culture from drifting so far that the mission goal stops mattering? The people who step onto the ship at launch might care deeply about Proxima b. Their great-great-great-grandchildren might not. You have to ask very uncomfortable questions. How do you prevent a group on board from deciding that turning back or changing course is better, even if it means wasting centuries of effort? What happens if a future leader declares that the original mission was a mistake and redirects resources to some internal project, like building more comfort or waging internal conflicts? In a closed metal world, how do you enforce laws when every violent conflict risks damaging vital systems? You are not just fighting conflict, you are fighting stagnation and decay too. Maybe one generation stops maintaining a critical system properly. They still get by, the ship still runs, but a century later, the damage shows up as a failure in life support or a loss of key knowledge. Technology and skills can actually regress in a closed environment if education fails and records are lost or corrupted. So you do not just need hardware redundancy, you need knowledge redundancy. You need to engineer culture, education systems, social norms, governance structures, all designed to keep the mission goal alive and the ship functional across dozens of human lifetimes. So when someone casually says, "We'll just send a generation ship," the reality is this. You are committing to 2,000 years of controlled social evolution inside a pressure hole. You're asking an entire moving society to hold on to a purpose set centuries before they were born, and you are trusting them not to break the ship, not to walk away from the plan, and not to tear each other apart under stress. That is not a minor detail. That is the core of whether the whole concept works. But even with all those problems, generation ships still matter to the Proxima timeline. They show that too slow doesn't automatically mean forever impossible. If your civilization thinks in spans of millions of years, a 2,000-year trip is long, but not insane. From that viewpoint, the real question stops being, is the trip time too big? And turns into, are you stable enough, coordinated enough, and mature enough to launch something that will only pay off for people who see you as distant ancestors? So when generation ships and cryogenic dreams fill a specific role in the story, they are the fallback path if you never crack high fraction of light speed propulsion. They say, even with slow engines, Proxima b is not unreachable. It's reachable at a cost, not just in energy and materials, but on social control, ethics, and long-term responsibility. And once you accept that, you have to confront another ugly layer. Even if you solve the ship and the society, space itself between here and Proxima is not empty, and at high speed, the empty part becomes dangerous. You worry about the engine, the fuel, the reactor, but there's another problem that doesn't care what drive you use. Between you and Proxima b are 40 trillion kilometers of almost nothing that stops being harmless the moment you go fast enough. Start with the basic question. What is actually in the way? Space is not a perfect vacuum. In the region between stars, the interstellar medium, there are on average around one hydrogen atom in every cubic centimeter, plus a tiny amount of helium and a small population of dust grains. 1 atom per cubic centimeter sounds like nothing, but remember the scale. You are crossing around 40 trillion kilometers, roughly 25 trillion miles. Multiply that thin gas over that huge distance, and your ship will plow through a staggering number of particles. At low speeds, like the 10 to 20 kilometers per second of today's probes, those single protons and atoms just drift by. They hit the hull with such low energy that you can treat them as background. But once you start talking about 10% of light speed, around 30,000 kilometers per second, those same single protons and atoms become high-energy bullets. In the ship's frame, each one smashes into your forward shield with energies high enough to chip away material and generate radiation. Over years of travel, that adds up to serious erosion and serious dose. If single atoms are already a problem at high speed, what happens when you meet something bigger, like dust? A dust grain in interstellar space might have a mass around a trillionth of a kilogram. That's 10 to the minus 12 kilograms, about a millionth of a milligram. On a table, that's invisible. At 10% of light speed, that grain hits your ship with kinetic energy you can estimate using the usual formula, half the mass times the square of the speed. When you plug in the numbers, you end up with hundreds of billions of joules of energy per kilogram of dust. That's comparable per kilogram of projectile to the energy release you see in nuclear weapons. You don't want that punching straight into the crew deck. So any serious starship design has to accept that the front of the ship is consumable. You need sacrificial shielding, thick layers of material whose job is to absorb these hits and slowly get eaten away. You might place the living areas behind large tanks of water or ice, because water both absorbs radiation and can be replenished. You can use strong magnetic fields to deflect charged particles away from the hull, so they spiral around the ship instead of hitting it. People have also suggested ram scoop designs, where you extend the field or a physical structure ahead of the main ship to catch and deflect dust before it reaches critical systems. All of this costs mass, power, and complexity, but without it, at high speed, the front of your ship effectively sits inside a continuous micro-explosion zone. So how sure are you about what's out there? This is where actual measurements from Voyager 1 matter. Voyager 1 has already passed beyond the heliopause, the boundary where the solar wind's influence effectively ends and the interstellar medium begins. Its instruments have recorded plasma densities, magnetic fields, and particle fluxes in that region. What those data show is that interstellar space is not just a smooth, thin gas. It's denser and more structured than simple early models assumed. There are variations, clumps, and changes in density and magnetic field strength. For a starship, that means you can't just assume one clean, uniform number for how much stuff we hit per cubic meter. You have to design for the worst patches you might cross. Voyager's readings give you a lower limit on the kind of shielding that will be needed. If the local bubble around the sun is already a bit more crowded and dynamic than you thought, you have to expect similar surprises on the way to Proxima b. That directly feeds back into how thick your shield must be, how strong your fields must be, and how much structural margin you need. Apart from dust and normal particles, there is another layer of threat that does not go away no matter how slow you go: cosmic rays. These are high-energy particles, mostly protons and atomic nuclei launched by supernova explosions and other violent events far away. Even in Earth orbit and on the way to Mars, mission planners worry about cosmic ray exposure for astronauts. At interstellar distances with no planetary magnetosphere and no thick atmosphere, you face continuous exposure for decades. A crew spending 20, 50, or 100 years in deep space needs serious protection. You can use water walls, tanks, hydrogen-rich materials, or regolith-like shielding if you can carry it. You can design bunkers inside the ship where people shelter during spikes in radiation. You can consider active shielding, strong magnetic or electric fields that deflect charged cosmic rays, but all of this adds weight, and again, every extra ton of shielding is another ton your propulsion system must accelerate. For a 2,000-year generation ship, the medical picture is even harsher. You're exposing multiple generations to chronic low-level radiation and occasional high spikes. Without excellent shielding and medical countermeasures, cancer rates and genetic damage become major concerns. Now tie this back directly to speed and travel time. The faster you move, the harder the interstellar medium hits you. At low speeds, dust and gas are mostly a radiation and erosion problem over very long times. At 10 to 20% of light speed, each impact is individually dangerous, and the rate of impacts goes up because you are sweeping more volume per second. The energy in each collision grows with the square of your speed. Double your speed, and each impact is 4 times more energetic. So there is a practical limit where just go faster stops being an answer and becomes a liability. That means there's probably a sweet spot for Proxima missions. It is not literally as fast as the drive allows, it is as fast as you can go without turning the front of the ship into a self-destructing blast furnace. For tiny gram-scale Starshot probes, you can accept enormous risk because losing a few chips does not matter if a few survive. For a 1,000-ton fusion ship with a crew, the acceptable risk is very different. You may end up preferring a speed around 10 or 20% of light, not because your engines cannot push harder, but because above that, dust and gas make the mission much more fragile. And here's the uncomfortable twist. Even if you solve propulsion, shielding, and biology, you're still aiming at a target that is itself moving through the galaxy. The longer your trip, the more it drifts, the more your shot can miss, and the more the system can change while you're en route. Surviving the ocean between you and Proxima is one part. Hitting a moving planet at the far end after decades in that environment is another challenge entirely. You're not shooting at a fixed bullseye painted on the wall. You're trying to hit a pebble that is orbiting a moving star while both your launcher and the target are racing around the galaxy. That's the navigation problem to Proxima b in one line. First piece of bad news. Proxima Centauri is not sitting in space waiting for you. It's moving through the galaxy at tens of kilometers per second, relative to the sun, something like tens of thousands of kilometers per hour. Tens of thousands of miles per hour. Over 20 to 50 years, that adds up to billions of kilometers of drift, billions of miles. If you point your ship at the position you see Proxima today, by the time you arrive, the star system will be somewhere else. So from day one, you're aiming at where it will be, not where it is. Your launch solution is basically aim at a point in space that doesn't exist yet and trust your math. So how do you do that without just guessing? You lean on astrometry, precise measurements of where stars are and how they move. Missions like Gaia map the positions and motions of stars down to micro-arc-second precision, tiny fractions of a degree. That lets you measure parallax, the apparent shift in position as Earth orbits the sun, and proper motion, the star's drift across the sky over years. From that, you get a three-dimensional velocity vector for Proxima Centauri in kilometers per second in both metric and, if you like, miles per hour. When you carry those numbers out to 4.2 light years, even tiny angle errors turn into big linear distances. Micro arc seconds at that range still correspond to uncertainties of millions of kilometers, millions of miles. That sounds scary, but remember, your ship is not a bullet with no steering. If you build in the ability to correct course mid-flight, those errors are manageable. The key is that your map of where Proxima will be in 20 or 30 years must be good enough that your corrections are small tweaks, not gigantic sideways burns. Now push this into the high-speed regime. Suppose you manage a cruise speed of 20% of light, around 60,000 kilometers per second, about 37,000 miles per second. At that speed, a 1-degree error in your initial aim is a disaster. Over the course of the trip, that slight mispointing sends you light months away from the target, billions and billions of kilometers off course. Even a fraction of a degree can be enough to miss the entire system. So your navigation plan can't be fire and forget. You have to hold back some delta V, some sideways maneuvering capability, to nudge your path back towards the moving target as updated star position data comes in. For fusion rockets, that lateral delta V means extra propellant mass. For light sails, it means you must be able to tilt or curve the sail and reposition the laser beam extremely precisely, so you can bend the trajectory mid-boost. If you don't budget for this, navigation errors directly turn into wasted decades. You launch at enormous cost, you miss by a tiny angle, and your probe spends the rest of its life flying into empty space with nothing to show for it. And remember, you're not even aiming at a single point called Proxima b. The planet is orbiting its star. You know its presence from radial velocity data, from the way it makes Proxima Centauri wobble. That gives you its orbital period, about 11.2 Earth days, and a minimum mass and some idea of its distance from the star, about 7.2 million kilometers, about 4.5 million miles. But things like the inclination of the orbit, the exact three-dimensional orientation of that ellipse in space, are much less certain. So your ship can't literally aim at the planet because you don't know its coordinates to kilometer precision. You aim at a volume of space around the star, big enough that when you arrive, you can search within that zone and lock on to the planet's real position. That means you want the ability to adjust your trajectory inside the Proxima system, not just on the way there. You might need to do a small braking or turning burn near the star, or for a light sail, rotate and use the star's light and gravity to bend your path. All of that costs maneuvering capability, which you have to carry or design in from the start. Then there's the slow drift of knowledge back home while you fly. Our measurements of Proxima B's orbit aren't frozen. As observatories on Earth and in space gather more data, the estimates of its mass, its orbit, and even the possibility of additional planets in the system can change. New analysis might reveal a second planet in the habitable zone or show that Proxima B's orbit is more eccentric than we thought. Stellar activity cycles could shift our estimate of how violent the flare environment is. Every time a new Gaia data release comes out, your picture of where exactly the star is headed can sharpen. If your mission takes thousands of years, none of that matters. The ship will be long gone, and any new information is just academic. But if your flight time is 20 to 100 years, these updates are happening while the ship is in transit. You have a moving target in two senses. The star and planet are physically moving, and your best model of their motion is also moving, as new data refine it. That gives you a planning loop you cannot ignore. Before launch, you aim using the best astrometry you have. During the trip, you keep listening for updated star position and orbit solutions transmitted from Earth. If your ship has onboard AI and maneuvering capability, it can adjust its path based on that stream of revised information. The shorter the trip, the fewer major updates you will see. The longer the trip, the more chances there are that the target coordinates, or even the definition of most interesting target in the system, will change under you. This is where travel time and navigation lock together in a subtle way. The longer your journey lasts, the more the real system can surprise you. Orbits can be revised, additional planets can pop up, the star's flare pattern can shift. In the worst case, you could discover mid-flight that the planet you were aiming at is less interesting than a newly discovered neighbor, but you do not have the maneuvering margin to change course. In contrast, faster missions tighten that feedback loop. A 20-year high-speed probe can be aimed using data gathered in the decade before launch, with only modest updates needed mid-flight. A 40-year or 60-year mission can still adjust to new orbital solutions and system discoveries in something like real time. You are more in sync with the system you actually measured, and less at the mercy of slow, decades-long corrections. So navigation to Proxima b is not just pointing and boosting, it is predicting where a moving star and an orbiting planet will be decades from now, steering through a dirty and dangerous medium, and keeping enough control authority in your back pocket to correct for every tiny miscalculation. And the longer your ship is out there, the more chances the universe has to move the goalposts, while you are stuck already mid-kick. You can solve propulsion, navigation, shielding, all of it, and still hit a hard wall at the very end, because getting to Proxima b fast is only half the job. The other half is ugly. You have to slow down again without destroying what you sent. Take the cleanest case first, the Starshot style probe. A gram-scale sail pushed to about 20% of light speed, roughly 60,000 kilometers per second, reaches Proxima in around 20 years. That sounds perfect until you ask, how do you stop it? The answer for that design is simple: you do not. The probe flies into the Proxima system at a huge fraction of light speed, crosses the zone where the planet is in minutes, maybe seconds of useful data collection time, and then vanishes back into deep space forever. It grabs a strip of images and measurements on the way through, sends them home, and that's it. If you want a rendezvous instead of a scream-and-go flyby, the physics turns on you. To stop relative to Proxima b, you have to get rid of almost all the speed you worked so hard to gain. In terms of energy, that means this. If you spent some large amount of energy to accelerate your craft up to its cruise velocity, you must spend roughly the same amount again to slow it back down. The kinetic energy, the energy of motion, scales with the mass of your ship and with the square of its speed. Double the speed, quadruple the energy. So if, say, you dumped 10 big units of energy into speeding the ship up, you need about 10 more to kill that motion when you get there, unless you can dump that energy into something like a sail and let the environment do the braking. That's why people look so hard at ways to let the target system itself help you. If you can lean on the starlight, the star's gravity, the interstellar medium, or the stellar wind to slow you down, you don't have to carry all your braking energy on board. You trade propellant tanks for smart interaction with what's already out there. One of the main tricks on the table is photogravitational braking, which sounds fancy, but the idea is straightforward. You use a very large, very lightweight light sail, hundreds of meters across or even more. On the way out from Earth, you might be pushed by a laser array. Then, as you approach the target star, you flip the sail and let the starlight itself push against your direction of motion. At the same time, you fly a carefully tuned path through the star's gravity field so that its pull and the light's push combine to bend and slow your trajectory. Instead of zipping past once, you let this combo gradually bleed off your speed. Studies show that with insanely low mass per square meter and huge sails, you can use this method to turn what would have been a 20-year, 20% of light speed flyby into an actual captured orbit or slow pass. The price is time. For Alpha Centauri, numbers around 100 years total travel, launched to capture, appear in the literature. Apply similar logic to Proxima and you're in the 100 to 120 year band. You go slower, you arrive with far less relative speed, and you can actually hang around the system, but you've just stretched the mission out by a factor of 5 compared to a pure fast flyby. Another braking tool people talk about is the magnetic sail, or plasma sail. Instead of relying on a reflective surface for light, you deploy a huge magnetic field in front of your ship, generated by coils or superconducting loops. That field interacts with charged particles in the interstellar medium or in the stellar wind near your destination. As those particles try to cross the magnetic field, they're deflected, and that transfer of momentum acts like drag on your ship, slowing it down. You're not wasting propellant, you're using the thin plasma around you as your braking medium. The good part is, it trades propellant mass for electromagnetic hardware. Once you have the coils and power supply, you can drag against the medium for as long as you want, as long as there are particles to push against and power to keep the field up. The bad part is, its effectiveness depends heavily on two things: your speed and the density of the medium. It works best when you're still moving fast and when the plasma density is reasonably high. That means it can be great as a first-stage brake, knocking off a big chunk of your speed far from the star, and then you might switch to other methods like light sails or conventional engines closer in. All of this circles back to the core timing question. If you only care about touch, grab a snapshot, and leave, then you can optimize for raw speed. Pump the ship to 20% of light speed, get to Proxima in 20 years, except that you have minutes at most to observe. For a wafer-scale probe, that might be fine. But if your goal is to go into orbit, map the system carefully, maybe drop landers or atmospheric probes, you can't arrive screaming in at that speed. You need to shave off velocity in a controlled way that doesn't cook your instruments or, in a crude case, kill everyone on board. That is where braking quietly takes over the schedule. A mission profile might look like this: 10 to 20 years accelerating and cruising, then decades spent bleeding off speed with sails, magnetic drag, or long low-thrust burns, and finally a careful, slow approach to Proxima B. Suddenly, the headline 20-year trip turns into a 100-year or 200-year rendezvous mission when you include the slowdown. You can shorten the coasting time by going even faster in the first half, but then the braking challenge gets harder and the impact energy you have to get rid of gets larger, squaring with speed. So even when your engine can push you to absurd velocities, the practical question is not just how fast can we go, but how fast can we afford to be going when we try to stop near a fragile target planet. Braking does not care about your excitement. It cares about the square of your speed and the thin, dangerous environment around your destination. And once you finally manage to arrive, slow, lined up, and alive, you run into one more hard limit you cannot hack. Even with the best engine, you still have to wait for light itself to carry your success back home. You can fight the rocket equation, you can fight radiation and dust, but there is one delay you cannot touch at all: the speed of light itself. No matter how advanced your engine is, your messages never outrun that limit. Start with the hard fact. Even if your ship somehow flies almost as fast as light, your signals do not get any bonus. They still move at the speed of light, and nothing faster. Proxima b sits about 4.24 light years away. That means a radio signal or a tight laser beam takes 4.24 years one way to cross the gap. Not months, not days, years. So if a probe over there sends a hello today, you will hear it more than 4 years later. If you answer right away, your reply arrives more than 8 years after the original event. There's no real-time control from Earth. Mission control becomes mission archive, watching the past, not steering the present. Then you run into the next constraint. It's not just delay, it's also how much information you can push through that gap. Signal strength drops with distance, and it drops fast. Double the distance, the signal is spread over 4 times the area, and so on. Over 4 light years, the beam from a tiny transmitter spreads out into a huge sphere. By the time it reaches Earth, the energy per square meter is extremely small. So you have to trade between 3 things: bandwidth, power, and distance. If you want a high data rate from Proxima, you need a lot of power at the transmitter, a very tight beam, and gigantic antennas or telescope arrays at the receiver. For small interstellar probes like the gram-scale Starshot chips, you can't carry big power sources or big dishes. Realistically, those crafts will send back tiny trickles of data, not full HD video streams. They will heavily compress images, pick only the most important measurements, and pack every bit with error correction so that even a handful of photons coming in per second to Earth's telescopes can be decoded. You get a few still frames, a bit of spectra, some key numbers, not a continuous live feed. For bigger robotic probes, maybe ton-scale vehicles with reactors or advanced power systems, you can do more. You can push higher power into a laser, you can stabilize a narrow beam, and you can target massive optical receivers back home. But the basic geometry doesn't change. 4 light years means you're fighting a harsh inverse square drop in signal strength, and that forces every message to be carefully planned and efficient. Now, think about what this means for crewed missions. A ship headed to Proxima b cannot treat Earth like a remote help desk. You cannot stop the ship mid-flight to ask, "Should we run this repair?" and expect an answer in time. Every question you send takes 4 years to arrive. Every answer comes back 4 years later. Life support failures, reactor glitches, navigation issues, they all have to be solved on board, by the crew or by onboard AI. So a crewed starship is not just a vehicle, it's a sovereign fragment of civilization. It needs its own command structure, its own medical and engineering expertise, its own decision-making rules, because by the time Earth finds out about a crisis, the crisis has either been solved or killed everyone. Even higher-level choices cannot be micromanaged from home. If the ship arrives and finds that Proxima b is a dead rock, but another planet or moon in the system looks more promising, the crew can't wait 8 years for a committee on Earth to debate options. They have to decide, in that system, with the information they have. You're not sending representatives you can override. You're sending a branch of humanity you'll only talk to on decade-long loops. Then there's the background noise. Proxima Centauri is already under radio watch by projects like Breakthrough Listen, which scan for artificial signals and map the natural radio environment. Proxima flares. It throws out charged particles, X-rays, ultraviolet bursts, and all of that activity changes the plasma conditions around the star. All of that affects how radio waves and possibly even tight laser beams travel near the star. Certain frequencies may get scattered, absorbed, or distorted during big flare events. So if you're designing a communication link from a probe in that system back to Earth, you need to know how noisy the star is, how often it flares, and which frequencies stay clear enough to use. You may choose to use optical lasers instead of radio to cut through some of that mess, but then you need ultra-precise pointing and large telescopes at both ends. Either way, the radio and plasma behavior of Proxima is not just an astronomy detail. It directly shapes how you design your deep space phone line. Now, fold all this back into the original question. How long until we know what Proxima b really looks like? You can't just say 20 years of travel or 50 years of travel and stop there. You have to add the signal delay. A high-speed Starshot-like flyby might reach Proxima in about 20 years. It snaps its pictures in a fraction of a second, processes them, and starts transmitting. Those photons crawl back to Earth over 4.24 years. So from launch to first real image on a screen on Earth, you're looking at roughly 24 years. If you instead plan a slower rendezvous mission, maybe a fusion-powered probe that takes around 50 years to arrive and then enters orbit, your first solid confirmation that it even made it into the system does not reach Earth until nearly 55 years after launch. Any detailed mapping, multiple passes, or lander deployment pushes useful science results even further out. You always add the light time on top of the travel time. That is the communications piece of the Proxima clock. It says even in the best case scenario, even with aggressive propulsion and perfect navigation, the universe forces you to wait. The star does not care how impatient you are. You can move hardware faster, you can compress data harder, but you cannot make information outrun light. And that delay feeds directly into the last uncomfortable layer of this whole question. Not just how long it takes to get there or to hear back, but how long it takes before you, as a species, decide you are actually going to build any of this for real. If you actually started building today, not talking, not simulating, but pouring metal and money into hardware, when would anything from Earth realistically reach Proxima B? 10 years? 100? 1,000? You can finally stop talking in pure theory here and line up a few honest timelines. Start with the softest scenario, the one that only leans a little beyond what you already know how to do. Take advanced nuclear electric propulsion, high-power ion drives, maybe some fusion-adjacent tech like fusion-boosted electric systems, plus aggressive miniaturization and strong onboard AI. None of that requires magic, just decades of serious investment. With that toolbox, you can imagine robotic probes that reach around 1 to 5% of light speed, so roughly 3,000 to 15,000 kilometers per second, about 6.7 million to 33.5 million miles per hour. At 1% of light speed, the 4.24 light-year gap to Proxima becomes a trip of roughly 400 years. At 5%, you're down to around 80 to 90 years of flight time. These are big ranges because the exact profile depends on how long you accelerate, how you brake, and what you are willing to risk. But in all cases, you're not seeing results in a human lifetime. If you launch the nuclear electric probe in the late 21st century at 1% of light speed, the people who approved it are gone long before it arrives. Your civilization might still be around to get the data, assuming you maintain continuity across 4 or 5 centuries, but no individual person plans their life around that. So if you want a Proxima mission that actually fits inside one career, you have to be more aggressive. That's where Starshot class beamed light sails come back in. If humanity decides to throw real, sustained resources at building a multi-kilometer laser array and manufacturing thousands of wafer-scale probes, you can push payloads to around 10 to 20% of light speed. That's 30,000 to 60,000 kilometers per second, about 67 million to 134 million miles per hour. At those speeds, travel time drops hard. 10% of light speed gives you around 40 plus years to Proxima. 20% cuts it to roughly 20 plus years. Then you always add the 4.24 years of light time delay for the signal to come back. So a 20-year flyby mission becomes roughly 24 years from launch to first image on Earth. A 40-year mission becomes around 44 years before you actually see what the probe saw. That's the first scenario where you can say, without lying, that people alive at launch could still be alive when the first data come back. A grad student working on the initial designs in their 20s might be retired or near retirement, but still breathing when the results hit. That shrinks the Proxima question from what will our distant descendants see to what might we ourselves see if we start now and keep going for a few decades. The obvious follow-up is, can you get that kind of timeline and still do something more than a screaming flyby? That pulls you back toward fusion, but now not as a distant abstract, but as a mature, routine piece of infrastructure. If fusion power becomes as normal to you as jet engines and gas turbines are now, then building fusion-driven starships is not science fiction, it's just another oversized engineering project. In that world, you can think about ships cruising at 5 to 10% of light speed, but this time with serious braking stages built in. At 5% of light speed, 30 years of cruise plus time to accelerate and decelerate lands you in the 40 to 50-year total mission band. At 10%, it's more like 30 to 40 years. Add the communication delay and you're still looking at something in the 40 to 80-year range between launch and confirmed arrival, plus first detailed data. That's not a 21st century plan. That's a civilization that's had fusion power, high radiation materials, autonomous systems, and heavy space industry for a long time. That looks like a 22nd or 23rd century play, where building a fusion interstellar ship is painful, but no longer existentially weird. In that environment, 50-year rendezvous missions to Proxima b move from fantasy to the outer edge of high-risk, high-prestige national or planetary projects. Then you hit the hardest question. What about humans on board? Robotic probes can accept risk. They can accept multi-G acceleration, higher radiation doses, tighter margins. Humans cannot. As soon as you say crew, everything inflates. Mass, redundancy, shielding, life support, safety factors. Even if you have fusion drives, realistic crewed ships are probably stuck at the lower half of that speed band, somewhere around 5% of light speed, maybe a bit more for very short bursts. At 5%, you're talking 80 to 90 years of flight time if you include acceleration and braking. That's longer than one human lifespan. Even if medicine pushes healthy life into the 100-plus range, a crew that leaves in their 30s might arrive in their hundreds if they arrive at all. More likely, you're back in generation ship territory, with people being born and dying on the way. You go, your grandchildren arrive is not a joke line. It's the honest version of crude interstellar travel with anything short of extreme speeds. There is a chance that deep hibernation, suspended animation, or radical life extension could bend those numbers, but none of that exists at usable levels today. So for now, crewed Proxima missions are in the very far future, very high risk, very high cost box. Robotic probes, especially beam sails and future fusion designs, are the first realistic steps. Finally, there is a possibility a lot of people do not like to say out loud. There's a real non-zero chance that Proxima b stays unvisited forever by humans. Not because physics forbids the trip, but because the combination of energy demand, engineering complexity, will, and long-term stability always ends up just slightly out of reach. Maybe you never build multi-terawatt laser arrays. Maybe fusion power never becomes cheap and boring. Maybe your civilization keeps turning inward, spending on other priorities, or collapses and rebuilds repeatedly without ever sustaining a centuries-long project. In that timeline, you still learn more about Proxima b with better telescopes. You might eventually image its atmosphere, measure its climate, and map its continents from afar. But no human-built object ever flies through its sky. No robot lander ever touches its ground. It stays a permanent data point. The nearest may be Earth, always seen from 4.24 years of travel away, never confirmed in person. So when you ask, if we started building now, when could we arrive? The honest answer is a range, tied to how aggressive you are. With only near-term nuclear and electric drives, you're talking 80 to 400 years for robots. With Starshot-class beam sails, you can cut that to 20 to 50 years for tiny probes. With fully mature fusion, you might get 40 to 80-year rendezvous missions on the table. With crew, you're probably stuck with multi-decade to century-plus journeys. And wrapped around all of that is the uncomfortable final option. You never go at all. And that sets up the last, sharpest question in this whole story. Because at this point, the main barrier is not distance or equations anymore, it's you. Are you actually going to choose to become an interstellar species, or are you going to sit under one star and just talk about it forever? So what actually sets the clock now? Distance or you? On pure physics, the universe is giving you a hard challenge, but not an impossible one. The never feeling mostly comes from where you are as a civilization, not from some hidden law that forbids the trip. Start with the physics answer, stripped down. If you build multi-terawatt laser arrays on or near Earth and you master ultra-light gram-scale light sails, you can, in principle, push robotic probes to around 10 to 20% of light speed. That is roughly 30 to 60,000 kilometers per second, tens of millions of miles per hour. At those speeds, Proxima b is about 20 to 40 years of travel away. Add 4.24 years for the signal to get home, and you get a round number like 25 to 45 years from launch to first data. If you go the other route and rely on fully developed fusion with big, heavy ships and built-in braking stages, you're probably down in the 5 to 10% of light speed band. That gives you something like 40 to 80 years of travel time, maybe up to a couple of centuries if you go slower or carry more mass. So, on physics alone, the barrier is high, energy is huge, engineering is brutal, but there's no rule that says you can never reach Proxima b. It's not a forbidden zone. It's just expensive in the hardest possible way. Then you step down from physics into engineering, and the story changes tone. On the engineering side, you're nowhere near a ship that can do 10% of light speed, let alone 20. You don't have working fusion reactors and power plants, never mind flight-ready fusion engines. You don't have radiation shielding that's tested for decades at high flux in deep space. You don't have 100 gigawatt to terawatt class laser arrays sitting on mountaintops or in orbit with the optics and phase control needed to focus on a sail a few meters across halfway to the moon. Right now, your speed record is the Parker Solar Probe at about 0.00064 of light speed. Starshot's target, 0.2 of light speed, is roughly 300 times faster than that. And because kinetic energy goes with speed squared, that's not a factor of 300 in difficulty. It's more like a factor of 90,000 in energy per kilogram. Bridging that gap is not a matter of a few design cycles. It's a whole new regime of energy handling, thermal control, materials, and autonomous control. So the engineering answer to how long is you're still at the crawling stage. You know what you'd build in broad strokes. You have sketches for light sails, fusion drives, magnetic shielding, and AI navigation. But between those sketches and a real, tested interstellar-class vehicle, there are multiple layers of hard, expensive, failure-filled development that you haven't started at scale. Next layer down, the economic answer, and this is where the numbers stop feeling abstract. Breakthrough Starshot's rough estimates just to build the first serious beaming array and fly gram-scale probes sit in the tens of billions of dollars. That's in the same ballpark as a large national infrastructure project, a big warship program, or one country's annual space budget. Fusion starships or true generation ships are not tens of billions. They're civilization-level investments. You are talking about something comparable to a large fraction of global military spending or a large fraction of the global energy sector, sustained over decades. This is not a nice add-on to what you already do. It is a decision to move interstellar flight into the same priority class as war, power, and communication. So the real economic question is not, can you afford it in some absolute sense? The planet collectively already spends trillions every year on weapons, entertainment, and burning fuel. The question is, how long until you decide that sending a probe to Proxima b is worth as much sacrifice and focus as the other things you treat as essential? That choice sets the start date. The tech could be spun up in a few decades if you poured enough money into it. If you drip feed it at the level of one small research program, it will slide forever into later. Then there's the civilizational answer, the one nobody can calculate precisely, but that matters more than all the equations. If humanity avoids wiping itself out and keeps expanding its technological base for the next few centuries, the odds that you eventually launch a serious Proxima mission are high. On cosmic time, a 500-year delay between discovering Proxima b and visiting it is nothing. Stars live for billions of years. Orbits barely shift. From the galaxy's point of view, you either go now or a blink later. It is the same. From your point of view, 500 years feels like forever. It is 20 human lifespans stacked end to end. Whole languages shift in less time than that. Systems, even basic values, do not last that long untouched. So when you ask, how long until we go? Part of what you're really asking is, do we think we can keep a complex technological civilization intact and curious for centuries without dropping the thread? Put all of that together and you get the only honest punchline you can give in a video like this. When someone asks, how long would it take us to reach Proxima b, the straight answer has 3 levels. With today's tech, using chemical rockets and gravity assists, you are in the tens of thousands of years range. That is effectively never for humans. With near-future nuclear and early fusion systems, you could be talking centuries to a few millennia for large ships, and decades to a few centuries for smaller robotic scouts. With aggressive beam sails and fully mature fusion, you're looking at something like 20 to 100 years of travel time, plus about 4.25 years for the signal to come home. So the universe is not the thing stopping you. The laws of physics, as far as you currently understand them, do not forbid Proxima b. The real timer starts when you decide, as a species, that building starships is not a side project, not a thought experiment, but something you are actually going to prioritize, fund, and finish, even if the payoff comes long after you personally are gone. That is the real answer to how long. The distance is fixed, the speed of light is fixed, the variable is you. And the moment you finally decide that the first image taken from the sky of another star's planet is worth everything it will cost to get it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.